Good afternoon, class. We are looking at chapter 2 limits. Here's the second part of section 2.1 limits of sequences. Recall, in the case of arithmetic and geometric sequences, what we discovered. An arithmetic sequence is in this format: a sub 1, a sub 1 plus d, and so on, where the difference d between consecutive terms is constant. Recursively, we write it as a sub n plus 1 is a sub n plus d, and explicitly it's a sub n equals a sub 1 plus n minus 1 times d. And notice here we are adding 4. Similarly, a geometric sequence, a sub 1 r, a sub 1 r squared, and a sub 1 r to the power of n minus 1 is a general term, where each term is r times the previous one. Recursively, a sub n plus 1 is r times a sub n. Explicitly, a sub n equals a sub 1 r to the power of n minus 1. Notice this is 1 and multiplied by 4. So we are multiplying by 4. You get 4, 16, 64, 256, and so on. Now, in many texts, they use just a to represent a sub 1. So s sub n, the sum of the first n terms is a times 1 minus r to the power of n over 1 minus r. And if r happen to be between negative 1 and 1, then s sub n is a over 1 minus r. Let's quickly look at the proof. You're not responsible for the proof, but I just wanted to remind you what we have seen in algebra. And here's the geometric sequence added up becomes geometric series. A plus AR and so on is the summation. This is the summation notation sigma n equals 1 to infinity a r to the power of n minus 1. Needless to say, a can't be 0. So the first n terms, we write a plus a sub r, a times r plus a r squared, and all the way to a r to the power of n minus 1. Let's multiply both sides by r. So if I multiply this one by r, I get rs sub n. This becomes ar, this becomes a r squared, this becomes a r cubed. What happens to this one? Becomes a r to the power of n minus 1, and this becomes a r to the power of n. We want to subtract this line from this line. So let's subtract s sub n minus r s sub n. So when you subtract, notice a lot of things cancel out. So this one cancels this one cancels out this one, and this one cancels out this one. So you're left with the first one here, a, minus the last one here, a r to the power of n. From the left side, we take out the common factor of s sub n. And from the right side, we take the common factor of a. Divide both sides by 1 minus r. And that's a proof that s sub n is a times 1 minus r to the power of n over 1 minus r. So in the case of a geometric sequence, s sub n is summation of n going from 1 to infinity of a r to the power of n minus 1, which is a plus a times r plus a r squared. And therefore, the limit of this expression as n goes to infinity. That's when we go from 1 to infinity. Now, what happens if r is between -1 and 1, r to the power of n goes to 0. If r is between -1 and 1, r to the power of n goes to 0. And therefore, we get simply a over 1 minus r. So this goes to 0, and we get a times a over 1 minus r times, if you take the limit of the inside, this is 1, this is 0. So this piece gives you 1 minus 0, and we get a over 1 minus r. This is also the proof where r is between -1 and. Let's put this to a good use. We want to add the terms 1/2, 1/4, all the way to infinity. And the very first thing we notice is that this is a geometric sequence. If you claim something is a geometric sequence, if it's a arithmetic sequence, you got to come up with a couple of things. What is the first term? And then in the case of a geometric sequence, what is the ratio? So divide 1/4 by 1/2, 1/8 by 1/4, and you notice a is 1/2, so is r. Again, if you multiply 1/2, if you multiply this by 1/2, you get 1/4. If you multiply this one by 1/2, you get 1/8, and so forth. Therefore, because r is between -1 and 1, it's 1/2, we can use a over 1 minus r. So a is 1/2, so is r. So a is 1/2 over 1 minus 1/2. And this is 1. So the summation will result in 1. So 1/2 plus half of it plus another half and continues indefinitely results in total sum of 1. It's fascinating. Express 0.46 bar as a rational number. This has been done in algebra. You set this equal to x, then you multiply both sides by 100 and simplify and solve. You may remember it from algebra. We are going to look at it from a geometric sequence point of view because 0.46 bar, it's a repeating decimal, which means 0.464646. What this means is this part, which is 0.46, added to this part, which is 0.0046, added to this part, which is 0.000046, and it continues. You can write those numbers in the form of a fraction or decimals. Please understand, this part is 46 over 100 or 0.46. This part is 46 over 100 squared or 0.0046. And this part is 46 over 100 cubed or 0.000046, and it continues. By that, we mean 10,000, for example. So notice, you're dealing with the geometric sequence. The first term is this. Both formats, you can write it as a fraction, you can write it as a decimal. And or, notice, this is 100 times larger than this. If the denominator is 100 times larger than this, the fraction is 100 times smaller, or you can divide this one by this one, this one by this one, and notice r is 1 over 100 or 0.01. Because this is between -1 and 1, the sum would be a over 1 minus r. And we are going to write the sum as a over 1 minus r. Now, how do you write it? fractional format or decimal format. Makes no difference. We're going to look at them both. And by the way, I'm not interested in simplifying this because I want you to see where it comes from, okay? Now we're going to simplify the fraction. It's a complex fraction, so I'm going to look at it from the point of view of fraction and then decimals. How do you simplify a complex fraction? Multiply the top and the bottom by LCD, which is 100. So when we multiply these two, we get 46. When we multiply these two, we get 100 minus 1. So 46 over 99. If you go with the fraction, this is the answer. If you want to go with the decimal, you get 0.46 over 1 minus 0.01 is 0.99. These two numbers are the same. Of course, you never leave it as that. You have to change it to this. By the way, this can't be simplified any further and you're done. In other words, there's no common factor between the top and the bottom. .75 bar, basically we are concerned with this one, which is the repeating decimal. So we rewrite it as 5.7575 and we continue indefinitely. The repeating decimal follows the same process as the previous page. Meaning, this one is 75 over 100 or 0.75. This part is 75 over 100 squared or 0.0075 and so on. So we get this, meaning this part is this part. And for that repeating portion, we go with the geometric sequence where the first term is 75. And again, this is the decimal representation. Let me erase my work so it becomes easier to read. So this part with fractional format or decimal makes no difference. So the first term for this part, because we want to make sure we're dealing with this part, okay? This part is A equals this number, 75 over 100 or 0.75. And by the way, again, I don't want to simplify it to 3 over 4 on purpose. Everybody knows this is 3/4. It doesn't matter. You can keep it as that because I just want to make it. Now, R is the same as before, 1 over 100 or 0.01. And therefore, we can use this part, A over 1 minus R. So 5.75 bar is 5 plus 0.75 bar, and 0.75 bar, we are going to use that. So we keep the 5 and this part, A, either one, over 1 minus R, again, either one. So here's the fractional format, 75 over 100 over 1 minus 1 over 100, or a decimal format, this is 0.75, this is 1 minus 0.0. So first, let's look at the fractional format. This, again, is a complex fraction. You multiply by LCD, namely 100, the top and the bottom. And this part the numerator becomes 75. The denominator becomes 100 minus 1, which makes it 75 over 99. And this, everybody, is a fraction that has a common factor of 3 between the top and the bottom, becomes 5 and 25 over 33. If you were to use the decimals, you would use 0.75 over 1 minus 0.01, 0.99, and this is the same as this one. I hope you see that, okay? All right. Now this is done and you're finished. However, in some texts, when they say rational number or a fractional format, they just want a fraction. This, as you know, is a mixed number. So 5 times 33 plus 25, 190 over 33. They may want it in this format. Recursion for medication, the geometric recursion or sequence example is b sub n equals 3 times 2 to the power of n is 0, 1, 2. For this example, we want to see what do we get for the first few. That's the basic recursion we've seen, and then we go to medication. If you choose n to be 0, 2 to the power of 0 is 1, so you get 3. 1 is 2 times 3 is 6. 2 is 2, 2 is good. 4 times 3 is 12. If you put 3, 2 cubed, the 8 times 3 is 24. If you put 4, 2 to the power of 4, 16 times 3 is 48, and so on. So this is the same as this, where v sub n plus 1 is r v sub n, r is 2. By the way, you can see that from this formula if you want. R is 2, or just write 6 divided by 3 is 2, 12 divided by 6 is 2. So you can see that R is 2, and A or B sub 0 happen to be 3. Now, we want to modify this. Let's modify the geometric recursion by adding a constant term C. This difference equation arises for many real-world examples, such as when a patient is given some medication on a regular basis, daily or so, b sub n plus 1 becomes r b sub n plus c. So if you look at this one, we are adding a constant. This is like giving medication to patients. So what is r? The percentage of drug remaining in the body, the percentage, the portion, the fraction. C is the fixed amount of drug administered. So that means the amount of drug that we give to the patient at a specific time step. In which case now, this changes to this plus a constant. And the solution is the same thing, and it adds this factor of C times 1 minus R to the power of n over 1 minus R. And in some texts, we use A or B sub 0 as the first step. So I want to make sure that, everybody understand that. And by the way, I have the proof of this at the end if anybody's interested. Let's look at a simple example to make some sense out of this. Solve the difference equation b sub n plus 1 equals 0.8 b sub n plus 4, where b sub 0 is 5. When we say b sub 0 or a, and find what is the limiting value. Then that means after that, you want to take a limit. Okay. Before we solve this, anytime you're dealing with a case like that, you want to write the given, which means, class, you do this. You look at this one, and you compare it to this one. So obviously, b sub 0 or a is 5 is given. When you compare it, r is 0.8, lowercase c is equal to 4. So first, write the given. Why do we do that? Because if you go to this formula, now that is the solution, you are going to replace with what's given here. B sub 0, or A is replaced with 5, or is replaced with 0.8, and C is replaced with 4. So this is 0.2. Because we want to find the limit in the next step, here's the way you simplify this. You take this 0.2 and you put it underneath 4. It's the same thing. And 4 divided by 0.2 is the same as 40 divided by 2, or 20. Now, to simplify this, I hope you recognize this as some expression. You can even call it x. And if you do that, now you have 5x. You distribute, and this is like 5x. This is like minus 20x. They add up to minus 15x, just in case. Do you have to change it to x? Absolutely not. But if it helps you see it, it's a good practice. And now it's ready to be taken care of by taking a limit. So we are going to take the limit of this last expression. So the limit of a b sub n as n approaches infinity is the limit of this expression, 20 minus 15 times 0.8 to the power of n, as n goes to infinity. We use the limit laws. So the limit of 20 as n approaches infinity, minus 15, the limit of 0.8 to the power of n as n approaches infinity. This is just a number, a constant, the answer is 20. And 0.8 is between -1 and 1, or you can say between 0 and 1. And this limit goes to 0 because of that. So this limit, because of this, everybody, this goes to 0. So 20 minus 15 times 0, the answer is 20. So that's the limiting value. And again, bear in mind over here, B sub 0 or A was given as 5. Normally dealing with patients, normally it's 0 unless otherwise mentioned. A patient is injected with a drug every 12 hours. Concentration will be reduced by 90% before each injection, and the new dose increases the concentration by 1.5 milligrams per milliliter. Part A, what is the concentration after 3 dosage? Part B, write the expression for C sub n plus 1 in terms of C sub n, and so on. For concentration, they are using capital C. So first pay attention to that. Therefore, every B here changes to C. Now, before we answer this question, let's write the given. So every 12 hours, this is a time step. Very important number, but it doesn't enter anywhere in this formula. Concentration will be reduced by this much. So what is left is the rest of it. So B sub 0, we're going to call it C sub 0 or A 0 because we're dealing with the patients. And what remains in the body is 1 minus that, or 10%. And the amount that the amount of concentration that the new dose will be there constantly is 1.5 milligrams per milliliter. That's lowercase c. So this is the given. C sub 0 or A 0. R is 1 minus that. What remains in the body is R, 0.10%. And lowercase c is 1.5. So for the first part, let's make up a table. And the first one, C sub 1 is 1.5, right? What is the next one? Well, 10% of this remains, and then we add 1.5. So 1.5 and 10% of that. 10% of 1.5 is 0.15. They add up to 1.65. For the next one, we get again 1.5 and 10% of this one now, which is 0.165 added to 1.5, we get 1.665. Part B, write the expression for C sub n plus 1 in terms of C sub n. So this, we write it, and we change the B to C first. So B sub n plus 1 was R B sub n plus C. Now we're going to say C capital C n sub plus 1. C sub n plus 1 is R C sub n plus C. Now we use the given. Replace the R with 0.1. Lowercase c with 1.5. And we're done with this part. Find the formula for C sub n as a function of n. So we go back up here and change the B to capital C. So this one, everybody, is the same as that one, except we are using capital C. Now we are going to go back to the given. Replace the C sub 0 or A with 0, or with 0.1 and lowercase c with 1.5. We are going to work on this and simplify it. This is 0.9, and we put it underneath 1.5, which is 15 over 9, or 5/3. If we choose n to be 1, 2, 3 in this formula, we get the table that we made up here. 1, 2, 3. You can try. Now we want to find the limit of this last statement, last expression. So the limit of 5/3 times 1 minus 0.1 to the power of n, we use the limit laws. We take the 5/3 out, the limit of 1, as n goes to infinity, minus the limit of 0.1 to the power of n, as n goes to infinity. And we should know this is 0 because 0.1 to the power of n, when the base is between -1 and 1, this goes to 0. So the answer is 5/3. The units milligrams per milliliters. Okay, so we know where the limits come from. We're going to look at one more example. Any questions, class? A doctor prescribes a 100 milligram antibiotic tablet to be taken every 8 hours. Just before each tablet is taken, 20% of the drug present in the preceding time step remains in the body. How much drug is left after the third tablet? Write the expression for Q sub n plus 1 in terms of Q sub n, and so on. The moment we see Q sub n plus 1, that means instead of B, use Q, everybody. So before we start, we are going to write the given. We are dealing with patients and medications. B sub 0, in this case, Q sub 0 or A is normally 0. This is the lower case c, the amount of constant antibiotic that the patient receives, 100 milligrams antibiotic. This is a time step, doesn't enter any of the formulas. And just before each tablet is taken, 20% of the drug present in the preceding time step remains, or is 0.2 or 20%. So this is the given, everybody. And so we are going to make up this table. The first one is Q sub 1 equals 100 milligrams. After the second one, we get the same 100 and then 20% of that. 20% of that is 20, and we add 100, 120. Then the next one, we add 100, and 20% of this, which is 24, they add up to 124. So after the third one, the answer is 124 milligrams of antibiotic. We want to write the expression for Q sub n plus 1. We're going to write B sub n plus 1 and change the B to Q. Therefore, Q sub n plus 1 is R Q sub n plus C. We replace the R with 0.2, lowercase c with 100. So Q sub n plus 1 is 0.2 Q sub n plus 100. Find the formula for Q sub n. We look at this one and change the B to Q. And we use the given. We plug in Q sub 0 or A is 0, R is 0.2, lowercase c is 100. And we simplify this expression. So 0 times 0.2 to the power of n plus 100 times 1 minus 0.2 to the power of n over 1 minus 0.2. This goes to 0 because it's being multiplied by 0. This is 0.8, becomes the denominator of 100. This is 1,000 divided by 8, or 125. So the answer is 125 times 1 minus 0.2 to the power of n. If we put n equals 1, 2, 3, we get the table that we had in the first place. What is the limiting value? That means take a limit of that as n goes to infinity. So limit of the expression 125 times 1 minus 0.2 to the power of n as n goes to infinity. And again, we use the limit laws. We take the 125 out, and then limit of 1 as n goes to infinity, and limit of the 0.2 to the power of n as n goes to infinity minus that. And as you know, this is 1, this is 0, and the answer is 125 milligrams. You always write the units accordingly. So what is the limiting value of this concentration? It's 125 milligrams, which means no matter how long you continue, it will never ever go beyond 125 milligrams of antibiotic that they have found it to be okay as far as the patient is concerned. And beyond that, may be more harmful than beneficiary.